All right. Welcome everybody to today's webinar. It's on Icepak Solutions for Electronics Cooling. So this will be both a broad kind of overview and introduction to Icepak, as well as introducing you to a couple of the advanced techniques that Icepak offers. So my name is Conductivity. I'm a project manager here at Ozen Engineering. I've been here coming up on 6 years. And I've done a fair amount of Icepak work. If there's an Icepak training course or Icepak technical support questions, most of the time I'll be the guy handling that. And I just want to go ahead and show off the capabilities of this very powerful software. So first, a little bit about us. We are Ozen Engineering. So, I'm sure the attendees that are in-house already know some of this, but we are located in Silicon Valley. We have over 25 years of combined experience in FEA and CFD solutions, and we help our customers using our tools and provide best-in-class expertise for solutions to their problems. What do? We solve problems, multiphysical FEA, computational fluid dynamics solutions, and we are passionate about developing accurate simulations and realistic, core and realistic modeling as core competencies. So we think simulation is really important, and we're passionate about enabling the companies around here to do simulation at an advanced level. To help them, realize their unparalleled results. So we have a lot of different industries that we get into here in in Silicon Valley. Things like semiconductor, solar, and now automotive is becoming bigger, even bigger around here with Tesla and Apple and Google and everybody making cars now. So that's also something that we get into. And a couple of the tools that we use. Most of what we use falls under ANSYS. We've also developed interfaces between softwares that we sell, like Any2Ants, which is an interface between ANSYS and anybody musculoskeletal modeling tool. And we also do injection molding and advanced multi-objective optimization. And so the tools outside of the ANSYS portfolio we bring in, and we believe these are complementary and enhance the existing products in ANSYS. And here's just a snapshot of some of our clientele. And I think this is actually, I keep meaning to update this slide, but I think this number is 300 plus by now. But just a smattering of the logos that we work with. And these are, both our customers in either, consulting or software sales or training. We work with a lot of the companies around here to help them with their advanced simulation capabilities. So some of the industry-specific expertise, semiconductor, of course. We're in Silicon Valley. We do a lot of things in here. So things like a multiphysical simulation of semiconductor chambers, and these BGA package reliability simulations on the structural side. Also on the structural side, the thermal stress and seismic vibration. We do a lot of these different types of analyses here. We also get into MEMS quite a bit. MEMS is pretty big around here. And another big industry around here is a solar industry, and we bring the full suite of ANSYS analysis tools to bear for solar industries. So we can do both virtual prototyping through multi-objective optimization. We can do structural analysis like this wind load. This is a fluid structure interaction. And there's actually a wind load on a solar panel here, and we calculate the pressure, and then from that bring in the pressure as a boundary condition into a structural analysis and get deformation and force results. Also, design optimization. So multi-objective optimization, when you make simulations, when you make your simulations parametric, you can automatically vary all of the parameters within the limits that you define and evaluate it for a number of different things. So you can say optimize your design. You can make sure your design is robust and not over-optimized. You can do a sensitivity analysis and figure out which parameters are the most important, or maybe which parameters don't really matter, and for various outputs, not just one output, and not just a handful of parameters. Many parameters, many outputs. We offer the tools to make sense of all that. Also, electronics cooling. So this is also the topic of today. So some of the analysis types that we do. This is important for solder joint reliability, but also just thermal cooling, like a thermal characterization on the chip, board, and system levels. So it's a multi-scale, and companies may be involved at different parts of the process. One company may only be dealing in the chips, the others may be dealing with a device or even a data center. So we can handle all of these different length scales, something that we'll also be getting into. And consumer products, so drop tests, we have special tools as well to simulate drop tests, and we do a lot of this for our customers. It's something that they're interested in, both for consumer products as well as automotive products, like shown here. Biomedical industry, we have the coupling between musculoskeletal analysis software and ANSYS, so we can get realistic kind of muscle attachment forces on a bone, so we can evaluate the stresses on, say, an orthopedic implant under realistic boundary conditions. So that's something that we've done, and also we've developed a specialized software tool, like I mentioned before, that makes this process much easier. And injection molding. So injection molding is a difficult problem to solve without a specialized tool, but we do have a specialized tool, and we can simulate this, and it's something that is very common to use in consumer products as well as packaging, anything that deals with encapsulation or any of that. And it interacts with the structural analysis very easily as well. And this product is Planus 10, and we sell this and do work with this as well. It's a very powerful software. So we are Ozen Engineering, and we help our customers use their ANSYS to the fullest. Please visit our website for a list of future webinars, seminars, training. We have a lot of information up there, and yeah, just to keep abreast of events like this and other events coming up. So that's essentially it for the preamble. That was the company overview, and with that, I'd like to move on, just kind of introducing the position of Icepak, and give a general introduction to it. So this is kind of a table of contents for the webinar. After I introduce Icepak, I'll give some of the advantages of Icepak, say, over the competition, and then I'll discuss two Icepak applications that are on the more advanced side. So Icepak position. So the here's kind of a lot of the pressures on our customers today that we find. We have the product development market more competitive than ever. And we have all of these things weighing on our customers. And what this does is these constraints reduce really your margin for error. And so this means that you have to deal with things like uncertainty and complexity in a more systematic manner, or risk falling behind the competition because of these pressures. So the companies that are able to manage and make sense of this margin of error and keep on reducing that are the ones that are going to come out ahead. And this is the ANSYS, and this is our view on how you can do that. So we look at the typical engineering process as this line here. So we have on the x-axis, we have kind of a product life cycle, and the main difference here is in the cost of making a change to the product. So in the concept design, if it's just a sketch on the back of a notebook or just in a or just a picture, you can make a change to it, no problem. And as the process moves along to design detail, to physical prototyping and evaluation, to ramp up and full production, these changes get much more expensive to make, and they become more costly. And with the traditional process, we see the number of problems on the y-axis. With the traditional development, design and build and test it and see any problems, out on the field or in the prototyping phase. The majority of the problems you're not going to see until you physically made the thing and subjected it to whatever real-world environment it's going to be under. And then, so more recently, traditional CAD analysis and simulation have pushed this kind of the peak of this curve here further down, and then so we can reduce the total design change cost by finding these problems earlier, by doing simulation earlier on in the design process, and reducing the overall kind of design change cost, and then so it becomes much less costly to find the best product configuration. And the ANSYS vision is pushing all of these as early on as possible. While you're still in this design and concept stage, you can, with advanced simulation tools, find those problems, find these complex multiphysical, like kind of interrelated problems that may not be obvious. It's you can get most of the way to physically building and prototyping the thing in silico. And when you do that, it's exceedingly simple just to change a parameter in a sketch in a CAD tool, or vary a material design by just a drop down. Vary a material property by just a drop down and text input box. And then so this is our vision really for improving the development process. And so we accomplish this through the breadth of technologies approach. So from fluid to structural to EMAG and to systems. And ANSYS has the breadth as well as the depth to fully simulate your real-world product design. And for our area of interest for today, what we will cover in Icepak, and so Icepak is just one of the technologies offered by ANSYS, but I will discuss actually how it interacts with some of the other softwares in ANSYS. But for Icepak, just using it alone, it falls under essentially the thermal CFD side of this. So PCB thermal management, fan placement, heatsink design, some of these things are what it looks at. And then it can be easily used to do like a thermal mechanical stress, vibration, and drop tests and so on. So the thermal analysis, need. I probably not have to, talk too much about this if you're here, but it's a very demanding market to be in. You have the demands of miniaturization, things getting smaller and smaller. And you have IC transistor features shrinking down to 12 nanometers even, and and not only that, but you have handheld devices, not just maybe mainframes that may be as large as a room. You have handheld devices, and that's a very demanding environment for a product to be in. There's platform integration, more functionality is being packed into smaller and smaller space. You have these system on a chip kind of modules, and those really can do a lot of functionality in a small amount of space. And you have performance enhancements, higher speed, designing for high-speed channels, and wireless communication is also a challenge. And in addition to these miniaturization and performance increases, you'll have to do these more efficiently. So power consumption is also a big thing with going green or just going more efficient, due to like regulation, maybe reducing energy consumption. You have all of these kind of demands, and a lot of these demands are kind of in opposition to each other. And so that's kind of where the need for something like Icepak comes around. So Icepak, so just kind of in a very quick sentence summary, Icepak is the industry-focused tool for thermal simulation in the electronics space. So Icepak it falls under the general category of a CFD code, but it is built for that specific industry, and it has a lot of productivity enhancements for that industry that I'll be getting into here. So when you're doing this type of thing, it becomes important. So conjugate heat transfer. So conjugate heat transfer is something that only some CFD tools can do. So you kind of have, if you're doing FEA, you can model the solid. Excuse me. If you're doing FEA, you can model the solid, just fine in terms of thermal analysis. But for the fluids, you'll need to go with a convection coefficient, and you won't be capturing, some of the complex behavior if it's present in a fluid in FEA analysis. For CFD, if you just do a CFD fluids only, you'll be simulating the fluids domain, just fine. But you'll have to, do something like a heat flux. You'll have to have apply just kind of a heat flux to the boundaries of where the solid is, and it'll have to remove heat that way, and you won't really be simulating the actual behavior. And where the conjugate heat transfer comes into play is where it simulates both the solid and the fluid domain simultaneously, and you get a heat transfer between the two. And then so you don't have to have convection coefficients because you're simulating the actual fluid flow, and you don't have to calculate how much heat will be removed from the fluid domain by the solid because the simulation is simulating that. So that's something that Icepak offers, and it offers it in a very user-friendly way. And so what I mean by that, it takes a lot of the manual work away from you. So if you were to compare Icepak to a general CFD code, for things like the geometry, you would have to build whatever geometry you have, like say for like a package or something. You would have to build that over Boolean shapes. You'd have to create a sketch plane in your CAD tool and then extrude that, or revolve that, and then you have to do all the operations to kind of get the final shape in Icepak. And also for boundary conditions, same thing really. You'll need to specify the material properties and the kind of the various boundary condition types to really build up your code. So while these general CFD codes are powerful, they are really meant to simulate a wide range of problems. But where Icepak comes in is it has things like physical things that you'll be using in your simulation, like PCBs or a package or a heatsink object. It actually, or fan objects. It has these buttons in the user interface tool, and you press them and you just add them into your simulation just like that. So that's what the vertical integration means to your productivity. Instead of trying to model like a fan shape or trying to model like all the parts of a package, or and making those modifications for meshing and so on, Icepak has a lot of that intelligence built in. And for contacts and interfaces, so contacts and interfaces are are important for conjugate heat transfer, and for these in the general CFD codes, a lot of times they can be kind of some headache to create if kind of the automatic detection does not work. It becomes cumbersome if you have more than a couple different bodies to do these contacts and interfaces. But in Icepak, due to its geometry engine, it is kind of completely automatic. So that's another really nice productivity enhancement for Icepak. Do you have a question?
Oh, quick question. Does Icepak have, I don't know, a library of different fans, different type of fans, so I can pick up one other fan that I want to use?
Yeah, it has a library. So it has a library of fans. It has a library of heat sinks, of thermal interface materials, of just general like material properties as well, and of packages. It also has a fan object where you can enter in your fan curve. So if you have a fan that's maybe not in the library, but you have the fan curve, which is something very common to receive from manufacturers. All manufacturers have that. In Icepak, you can just put in a fan object, put in a general fan object, and put in your fan curve there, and just have it. So yeah, it does have a library of fans, and it also has a smart fan object to be kind of whatever fan you need it to be. So yeah, definitely. So that's one thing that Icepak, excuse me. So that's one thing that Icepak offers. The other challenge that Icepak is well suited to is it can do multi-scale simulations. So this is something that I mentioned earlier on in the simulation, but there are a wide variety of length scales in the electronics industry. So, the electronics industry, it's a very general term, really, but as you can kind of see from this slide, Icepak is up to the challenge. So everything from the micron level, when you're dealing with chips or packaging chips, to the PCB level, the board level, where you have a PCB board and you want to place a few chips on that board, to the full-on system level where you have a device or a room. Icepak can deal with all of those length scales, and it has specific features to help you go up and down this length scale. So if you want to simulate small features in Icepak, it has things like zoom in, which is analogous to submodeling in FEA. It has zoom in modeling that helps you do that. It also has non-conformal mesh interfaces. So maybe the very small and detailed mesh of one part of your analysis is not going to affect or propagate out into another part of your analysis. So that's what the non-conformal mesh interfaces are like. They're analogous to contacts in FEA. And for moving up in length in electronics industry length scales, it has things like 2D bodies. So 2D bodies do not have any thickness. So if you have a very thin layer of something, you won't have to worry about the mesh sizing in that normal direction. There won't be a mesh sizing. Icepak will simulate it with a 2D body. And you also have compact conduction models. And then so these are smart object functionality that Icepak offers to seamlessly and easily switch between more or less detailed representations of things like packages or heat sinks or fans. So with just a drop-down menu, it can switch between more or less detailed versions of those. So these are some of the features that Icepak has for moving between these length scales. And before I really go much further, I just want to show off the software a little bit and give you a sense of what the user interface looks like. So so over here I have ANSYS Workbench, and if you just want to use Icepak, it's just a matter of dragging and dropping Icepak onto the ANSYS Workbench project schematic. I can also launch this on its own. It doesn't have to be run from within Workbench, but when it's within Workbench, you get a lot of advantages. It can work with other tools and very nice and seamlessly. But that's essentially how you get to Icepak. And then if I just want to get into Icepak, I can double-click on it, and the interface comes up. And so it came up on my screen here. There we go. So this is the user interface for Icepak. And so the thing about Icepak, sort of in contrast to general CFD tools, you can do everything in this window in Icepak. If that's your workflow, you can build up the geometry and your entire model in Icepak. You can solve, and then you can also post-process all in this window. And that's actually what I'm going to show here. So it all happens in this window in Icepak, and so by default in an empty project, you only have what's called your kind of the cabinet. And this is just an empty space in Icepak, and it has an extent, but this is just kind of the extent of the sort of a fluid domain in Icepak. So if I just wanted to say simulate, I can do this. So this is just a package object. So if I just want to simulate a package, floating, in space here, I can, that's what I would be simulating here. I added a package object, and we can zoom into this package object actually, and we can, zoom into this package object, and oh, I lost it. Oh, okay. Yeah, it went down to the corner. Well, yeah, I guess so. I'll just use this another opportunity to show a really nice feature of Icepak. Unlike mechanical or other CFD tools, it has an undo feature. So whatever it is that I did there, I can move it back. So there we go. So this is a package object in Icepak, and we can make modifications to it. So I have, I clicked a button from the toolbar, and I can make a modification to it by editing the properties of this package object. And what we have here is, we have essentially a number of different forms. We have just basically a form. So this is like a very kind of a complex and detailed form. So I don't know if maybe people in the back or farther away can read it, but we can select the package type, and we have several different package types that it can be automatically here. We can change it. So right now it's a compact conduction model, so that means it is it has things like the solder balls and whatnot simplified out into kind of a bulk material properties, orthotropic properties. But if I wanted to, I can change this model type to detailed, and I can press update, and now it has, if you can't see it, these are solder balls. So it has these solder balls, each individual solder ball there in the geometry. So you can do something like that. And then if I want to just specify the dimensions of the package, maybe these form titles don't really make sense. For each of these I can view a schematic telling me what the various dimensions will be. So I'm in this overall dimensions tab, but I can go over to this substrate tab and change things like the material, top, bottom, like trace coverage percentages, and a number of vias, substrate thicknesses, and I can make sense of all these values with this schematic here. And same for the the solder. I can specify the number of solder balls and the material and everything, and die and mold here. And so while I'm here, I'm just going to take this opportunity to apply a power to this. And I'm also, because we're in a demo, I'm going to switch back to the simplified model of this and update. And that is essentially a package object. And if I wanted to, this is kind of ready to go. If I wanted to, I could just simulate this. I would just turn on gravity, and then I would mesh it. It can automatically be meshed, very easily. Yeah, it's like it's ready to go. I haven't turned on gravity. Not much will happen right now, but if I wanted to, I could solve it. But I can, do some more things. So I can add, say, a PCB object. So this PCB object also has a lot of good functionality. We can import, ECAD data, and it can import detailed trace material data, but we're not going to get into that here. But right by default, by the simple the simple option, it's just going to have an orthotropic kind of conductivity based on kind of the thicknesses I specify here, and I'm just going to specify these copper layer thicknesses in terms of ounce copper, and I'm going to put in something similar to kind of a standard JEDEC board here, and I'm going to do 30% conductivity for each of these. And yeah, I think that's it. I'm going to keep with the simple version here, but if I go detailed, I can add as many layers as I want. Have different thicknesses and materials for each layers, and I can configure vias. If I have the vias here, this will this will modify kind of there will be a special region here in the center of the circuit or in the center of the PCB by default, but I can move that around and it'll have different thermal conductivities based on the via information I put in. So it's really quite powerful. But I'm just going to do the basics. and simple update. And I'm just going to place the face center of this. That's a little bit hard to. It's a little hard to place the face center. Of that on the center of the PCB board. Okay, and so now it is aligned. So yeah, really what I can do is just to get things moving, I can do I can modify the edges of this cabinet, and I'm going to set the top, the max Y as an opening, and I'm going to set the minimum Y as an opening as well, and the air coming from the bottom will be ambient temperature here, and a static pressure, and coming out of the top, I'm not going to have the temperature boundary condition there, and then I can just turn on gravity.
Why gravity matters?
Well, because I'm not applying a forced convection flow, so this is going to be a natural convection problem, and in natural convection, as the air heats, it becomes less dense, and it rises to the top. So that kind of creates a temperature-driven flow.
Oh, wow.
Yeah. And so it can simulate that. And I'm just going to use the basic turbulence. I'm not going to use radiation, just because, it's. I just wanted to have something I can solve real quick. But I'm just going to go and solve this. And another thing that Icepak does is it actually uses Fluent as a solver. So if you could see my my taskbar here, it's using Fluent. This is the kind of a batch version of Fluent that's running in the background. But you don't have to look at this. You can look at these residuals here, these flow kind of solve residuals here. And this is, if you've done CFD before, you should be very familiar with these. Essentially, it has X, Y, Z, and a continuity and energy residuals that it needs to bring below a certain value in order to consider it solved. And so it goes through a number of iterations, and you may or may not be able to it may not actually get to our criteria by the time this solves, but it should get close enough so we can do some post-processing. But yeah, this is essentially what it does, and this is in serial, so this is running in serial mode on kind of an older laptop, and I believe the mesh size is yeah, so it's about 30,000 elements in terms of mesh size. And it's set to run for 100 iterations by default, and there it is, it's done. So if we want to post-process, we can just add post-processing objects. So I can say I want a contour plot of the package and the PCB, and I can tell it to show me the contours of those, and that's essentially it. So that's the temperature contours. I can also do a cut plane, and I can show temperature contours there as well. And I can show velocity. That temperature distribution looks a little bit weird. I may have done just a setup error in the, well, but the velocities look fine. Well, yeah. but I can do velocities here, and I can also do particle traces. And I can make these look a little bit better if I want. So I can do no to there and just do more. Yeah, so you can see kind of the direction of the airflow and kind of what it looks like, and a little bit of kind of low velocities circulation, recirculation there, and but yeah, that's essentially, so that's a very basic kind of look into what Icepak on a basic level looks like. And somebody mentioned library. It does come with a library. So the main library, so it's actually when you access it for the first time, it has a wide variety of materials. So these are kind of the materials that it comes with by default. It also has things like fans, blowers. It has PCBs, like VGA kind of components that are simplified. It has packages. These are full-blown package objects. Heat sinks. It has interface materials, and these are the interface. Yeah, it's interface materials, and TEC units as well for thermoelectric cooling. It can simulate those. So it has a wide variety of things, just out of the box. And so that's just, sort of, a quick look at Icepak, the basic functionality of what it looks like, so we have a sense of what we're talking about. So do you have any questions?
This is the use of the steady state problem.
Yeah. Yeah, it can solve a transient as well. Yeah. So that's okay. I think I went ahead 2 slides. Okay, so that is from Icepak. So one of the things we saw from the Icepak was a smart package object. So if you recall, I switched from compact conduction model to detailed, and this is kind of the transition that it did. It switched from this detailed view on the left here to this compact view on the right here. And the main difference in what it does is it has you have this kind of die attach and this die material and these solder balls. These the height dimensions of these, and in some cases kind of the widths of them will be small relative to your overall simulation domain. And what it did is it simplified those with these zero thickness plates. So it has these thin plates, and instead of these 3D physical bodies. And in Icepak, when you do that, thin doesn't just thin doesn't just mean really small. It means something specific, that there is no thickness in the direction, but it still takes special measures to simulate what's happening inside of that thermally. So in the flow equations, these faces here of this thin body, it will impede flow, going through that object. So it'll still behave like it would in the flow simulation, and then in the energy simulation, when it calculates the actual temperatures, it will have a shadow kind of mesh where it will do the thermal calculations on. And so it has both in-plane and a normal conductivity. Both of those will be taken into account. So the thin bodies are a really nice time saver. And the smart package object parameters, like I showed in the live demo, it has all of these things. It's basically, you can fill out and classify your package by filling out a form, basically. And that's with the smart package object. If you want if you want a little bit more control, you can get essentially the same thing, but with what's called a macro, and it can curate these components for you, and you can modify them, say if you have an exotic package. And another way to bring in your package into Icepak is, say, from an ECAD software. So a couple of these package types can only be brought in from ECAD software, like package on package and snack to die, but it can bring in the dimensions and also the this detailed kind of trace information from external ECAD softwares. It can bring those in, and you can see there's the package object. This is what we saw before, and it has these import buttons here, and that's essentially how it goes. You import it, you point it to the correct file, and then the file, it may or may not need the ECAD software to be installed for this to work, but that's essentially kind of what it's doing. So you can really has a lot of functionality to represent your package at the whatever level of detail that you desire. You can go all the way into having these small trace layers like this, or you can just use a compact conduction model, and maybe this is one of maybe 100 different packages in your simulation, and you can just use something like this. It's it's a fairly easy and user-friendly transition. And so that's one of many different smart objects. So all that functionality is just kind of under this kind of button here. And as I mentioned, there are several other different buttons, and a general theme of them is to have like a detailed and then a compact, computationally efficient mode for each of these. And it really saves a vast amount of engineering time. And so it allows you to adapt your components to whatever simulation scenario you're interested in. So if you're interested in modeling a room, you may not be interested in the fine details of every package. But if the package is really the only thing in your model, then you will a lot of times want that fine detail. So it's Icepak is despite the user friendliness, it's still a generally powerful tool. It allows you, it can model packages, new types of packages in different environments. It's not just a collection of forms that can't handle new scenarios. And so a little bit about the mesh in Icepak. I actually didn't show this, but the general approach of the mesh in Icepak, and it's incompatible with other types of meshing in ANSYS, is this structured grid mesh approach. And then so you can kind of think of these as 3D rectangular solids. And it's very efficient. It represents the entire domain as with these hexahedral kind of elements, you could think of them as, and it can transitions to different different size constraints. So in this we have two kind of blocks here, and we can see it has one size for the general background mesh, and then it has some size constraints to what it should look like near the object, and then it has different size constraints of what it should look like inside of the object. And it transitions to to these. It has these default sizing parameters created already, and it's a very efficient meshing method for in general. One thing that you can run into with this is because it's a structured grid. If you have, say, some elements that are very thin in one direction relative to the entire domain, because of the structured grid element, it's going to be, that size throughout the domain. So, here, these two blocks have been moved closer, and so in order to have, the specified number of elements between the gap in between these two blocks, it gets small in this horizontal direction here, and that small element size propagates through the domain. So because of this effect, it's becomes important in Icepak to kind of manage the length scales, and it has a lot of tools for doing that. So one of the things you can do is use what's called the non-conformal mesh interface, and in Icepak it's essentially like a contact in Icepak, and it allows the mesh to be discontinuous. So you could have something that is meshed very finely here, but in the background, it still has that relatively coarse mesh sizing here. So that's non-conformal interface, and it allows you to prevent mesh bleeding. Another advanced mesh technique that Icepak has is what's called multi-level meshing, and this is something that it gets from using the Fluent solver, and it's also referred to a hanging node technique. But really, the main thing about the multi-level mesh technique is this transition here. So it has 1, 0, 1, 2, and 3 different levels, and you can see there's kind of like a mini non-conformal interface here. It's what's called a hanging node, and it allows this mesh of basically hexes to get smaller and smaller, around areas that need it. So the parts of the model that need refinement are, have very refined mesh, and the parts of it that don't still have, the efficient and coarse background mesh. And then so you can kind of see the difference here on the left, a multi-level mesh versus a uniform fine mesh. It makes a threefold difference in the overall mesh count, just within, this domain around this fan. So that's a multi-level meshing. That's it's a really nice technology, and it's something that it gets by using the Fluent solver. Question?
Is this the same as assembly meshing in Fluent?
Yeah, that's what it's. Yeah. In the mesher, in the ANSYS mesher, yeah, you can do assembly meshing. Yeah.
Because I haven't been able to access this any other way. Is there something called the multi-level meshing in Fluent?
I mean, it is. So that's the only way to access this mesh method in the ANSYS mesher. In the Fluent, Fluent kind of has its own mesher, and you can do kind of the hanging node stuff within Fluent if you want. But yeah, currently that is the only way it's exposed in the mechanical mesher in ANSYS meshing. But yeah, that essentially, I think assembly meshing does more. Like it will automatically find the negative fluid region of a solid, I believe. But that's not involved here. But yeah, underneath it all in assembly meshing, it uses this hanging node approach. Yeah. So when we combine these two, we get flexible automatic meshing. So we can see we can mesh the complex parts of the model as need be. We can also have, for these exotic shapes like this, we can do kind of a multi-level meshing here, and then enclose it all in a non-conformal interface, and the rest of the model will be meshed as normal. So that's essentially, kind of a little bit on the Icepak meshing approach. And then so those kind of two things, the smart objects and the meshing, are some of the things that most of the other features, or a lot of the other features in Icepak will build upon. Wow, so 40 minutes already. Okay, yeah, and then just to go over some more Icepak advantages. So that's kind of the general approach of Icepak, and what makes Icepak different than the competition, the advantages that it has are as follows. So for one thing, Icepak is based on Fluent. So Fluent is the #1 CFD solver in the world, and it's a general purpose tool, but Icepak only exposes the capabilities that you need. So we kind of have this feature matrix of Fluent, and it really can do a lot, and it's very performant. It scales very well, it's very fast and verified, and all of that. And Icepak only exposes what you need to use as an electronics cooling engineer. And really every release, the Fluent, they do a lot of work on Fluent. So it pushes the boundaries of scalability. The ANSYS does a lot of work into the HPC with Fluent, and we can kind of see how it improves. R15.5, R15, and then how it it improves closer and closer to the ideal, and then even in the most recent release, it's getting closer. They're doing this benchmark is regularly done on a 32,000 cores or something, and we can see how close it is to an ideal speed up here when you get out into these a large number of cores. So it's not just kind of a checkbox in a feature. When you talk about scalability with ANSYS Fluent, you're not just going to see it just use all your cores, but maybe not increase your overall simulation speed. There really is a lot of work done by ANSYS in the Fluent solver in terms of performance, and Icepak gets to take advantage of all of that. Another advancement along that level is GPU technology. So when you use the coupled solver, Icepak has the capability to take advantage of the GPU to further reduce the simulation time. So without GPU, with GPU, we see a reduction of 2x. So really twice as fast for this setup here with the AMG solver. So Icepak can take advantage of this. Again, it gets the benefit of this great work done in Fluent. Icepak can also do advanced fan modeling. So for fans, it does have a fan object, and these take advantage of fan curves. And this is really something very popular and commonly done in the industry. But it also has the functionality or the capability to simulate, actually your 3D fan in the simulation. And it uses a multiple reference frame approach, and you can put a CAD model of your fan and simulate it as if it was spinning. So your mesh doesn't actually have to be moving, but it can simulate it as if it were moving. And for applications where swirl is very important, or where you have tightly packed components that may be very close to the fan, those situations may not match the kind of empirical setup where the fan curve was extracted from, and you may get inaccuracies. So the advanced fan modeling through the multiple reference frame approach of Icepak allows you to simulate that. Icepak also has advanced macros for data center modeling. So it has, so this is on the systems level modeling. You can create and set up and do approximations of kind of all the things I was showing before, and you can create and look at the flow for data centers. And you can look at failure scenarios, time-dependent analysis. You can perform parametric optimization studies, and you can simulate and set up things such as this very easily through the Icepak macros. So if you go to the macros, and then there's the data center components macro, you can set up things like the computer air room conditioning units or server cabinets. You can set up kind of perforated floor tiles and power distribution units. It has macros to set up all of these different things, so you can quickly and easily get a scenario going up to see how your data center will perform. So
how do you know these parameters are real? The parameters for a server is real.
So which parameters? I mean, the parameters are ones that you enter. So so you'll enter something like the flow rate, or the supply temperature, or the heat load, or its location. I mean, there are things that you'll enter, and then it'll create the geometry in the Icepak in the Icepak user interface that I showed. So you'll be able to see what it creates, and I mean, yeah, it's it'll be right there for you to see.
So to me, this sort of simulation is even easier than the simulation running on a circuit, because you don't need to worry about the small features. You only need to worry about the micro feature, like the heat property of a server.
Well, this is. Well, I mean, can you explain a little bit more?
Oh, we can talk about it offline.
Okay. Okay. Yeah. Yeah. But so this is the macro. So these macros like this help you set up your simulation more quickly. You also can do things like for the PCBs. When I showed Icepak, I showed just putting in copper layer, and then the thickness of the copper layer, and then kind of a percent coverage. But you can also have non-homogeneous material properties for PCBs and packages if you have your trace material data. So you can do something like trace import, and you can bring in trace data, and it's actually, so it's not going to model each of these little traces. It's going to create a separate material property mesh, and it's going to calculate the thermal conductivity in each direction on that mesh. So kind of this is the trace layers, And this is what the the location-dependent thermal properties, thermal conductivity will look like. And this is the top view, and this is the side view for a regular PCB board. So Icepak has the tools to help you do that. For zoom-in modeling, this is something that I kind of mentioned before. You have kind of an assembly of these line cards, and on the system level model, you can model them as a course, and then you can zoom in later and look at a more detailed simulation of just a single line card model using the calculated flow at the boundaries. And then so kind of what it looks like is system level model and then subsystem, and it'll automatically interpolate the boundary conditions onto the boundaries of your subsystem level model. For reduced order modeling, you can do things like extract a network representation of a package. So you can have a package, and then there's this DELPHI standard, and it's essentially a series of optimization cases to extract these resistance values for this circuit network here. It has the capability to do that. It has the electric CAD interfaces that I showed for and it works with a number of different interface formats. And another big advantage of Icepak is it's in the ANSYS ecosystem. So Icepak, doesn't just really work in a vacuum. It can, because it's in Workbench, it can be connected to each of these tools that you see here, and that allows you to do a more powerful and more realistic types of analysis. And this gets into that kind of depth and breadth that ANSYS, that we are talking about, because in your real world, you'll have more than one or two physics at play. And so here's an example of a motor here simulated, in a fully physical way. So here it uses the EMAG software Maxwell. And this particular example uses a Fluent, but that's essentially what Icepak is under the hood. And it also uses a steady-state thermal and then a static structural here in a structural. But so when you predict, just a single physical analysis, and you make the assumption of a temperature of 22 degrees, that's actually different than what the temperature would be with the full physics analysis. The three-way multiphysical solution has the magnet temperature at 53 degrees centigrade, and then so that results in a 16% drop in your predicted performance for this motor. So, and with your margin of error getting smaller and smaller, that 16% may not be something that is acceptable. That may be a huge surprise when you get out into the physical prototyping phase. So that's an advantage of Icepak, and it has a lot of different connections with different software tools. So SciWave is for a kind of signal integrity in PCB boards. It has two-way conductivity, two-way coupling with Icepak. So it sends kind of power losses to Icepak, and Icepak calculates temperatures, and then it sends temperature maps back to SciWave, and it modifies the power losses on the board based on those temperatures, and kind of sends that back to Icepak. And as you kind of get in this convergence loop here, and here's the SciWave, and here's the Icepak Icepak solution here, and there's really a macro in Icepak. This is done through a macro in Icepak. It's a setup, and it applies kind of the calculated power losses into Icepak, and then kind of the workflow is you can use this interface to calculate the power dissipation in SciWave, and then temperature in Icepak, and then export. And then here you can go further and export the converged temperatures to mechanical and do a thermal stress analysis after the Icepak and SciWave have converged. And so it has a similar coupling with HFSS. So here is an example of a problem in HFSS, and similar to Scalability, but it can just bring in the loss, the power loss into Icepak, and you can hook those up into a feedback iterator. Oh, it's not actually shown here. It's shown on the next slide. You can hook that into a feedback iterator, and it will actually, this will do sort of like a two-way kind of convergence. It'll update, and it'll send the information back and forth between the softwares until it reaches a certain criteria. There's just here, I just wanted to show there's the same kind of coupling between Icepak and Q3D as well. So you can really use Icepak to bring that thermal element to a lot of different EMAG types of analysis. And similar to Sentinel, so ANSYS acquired Sentinel recently, and allows you to bring in detailed kind of power maps for Sentinel. You can actually bring in temperature-dependent power maps and really get kind of the detailed heat dissipation of your chip. And I showed Icepak can interact with Design Explorer, so this helps you do multi-objective optimization. You can move from kind of a single point, and you can go past what if and actually get kind of a response and like kind of meta model of your simulation. You can get a reduced order model of your simulation, and from that you can do optimization and a bunch of other things. You can also do reduced order model with Simplorer, and this takes advantage of the linear time invariant capability of Simplorer. And basically how that works is if you kind of have a kind of a system of kind of things like this, and there are certain quantities that will kind of only be dependent on like a certain other quantities. So for each of these kind of two cylinders here, its temperature can be kind of predicted through time just by the inputs, just by the power distribution or something on that. And you don't really need to be running the full simulation every time to calculate these powers, as long as the flow doesn't change, and as long as they're not close enough together where they affect each other too much. You can make this assumption, this linear time invariant assumption, and Simplorer can actually extract that behavior. It can do a decomposition and extract that behavior, and you can get to the point where you can reduce the runtime of you can represent this simulation with a reduced order model, and you can run what used to take 2 hours in less than 2 seconds. So that's somehow how it kind of interacts with Simplorer. And with a structural analysis, again, it's within Workbench, and you can in Icepak you can calculate the temperature distribution, and then you can send that to structural analysis, and you can you can map that thermal the thermal results onto the mechanical analysis and do a stress analysis in mechanical. So you can combine them both that way, and that's very powerful. And it also works with a Design Modeler. So Design Modeler is a very nice preprocessor that you can use to kind of prepare geometry for Icepak. So if you have, say, a big assembly in SolidWorks or Inventor or Pro-E or whatever, Design Model is really nice, and it has specialized tools to help you prepare and simplify things in your CAD tool for Icepak. And then so it has things like it can extract a fan from 3D complex representation of a fan. It'll just make this a fan object that Icepak will know about. I can simplify the geometry, automatically from various levels into what are called Icepak primitive shapes. So it can do those, and it has several other Icepak specific functionalities for that. So and you can make changes in Design Modeler and update into Icepak, and it'll just modify just what you've changed. And yeah. So yeah. So that concludes the Icepak advantages. So I had two kind of specific applications that I kind of wanted to show, but I think I used up all my time. I'll just like really briefly show kind of some results from these. So this is a moving reference frame fan, and this is how fans are normally modeled. But with a moving reference frame, you have the CAD geometry of the fan. And so this is just a little bit of the background. You're not actually moving your mesh. You're just modeling the rotating fan as a rotating kind of domain. And then you have an interface, and then you have the stationary domain. And then you need to take advantage of the multi-level fan. You need to take advantage of the advanced Icepak meshing capabilities, and also advanced turbulence models, both of which it gets through using Fluent. And you can do things like you can reproduce a fan curve with this if you set up kind of the test setup, and you can kind of compare how the MRF fan to the lumped fan. And on the right here is the lumped fan, and you can see how for different kind of how this backflow region changes with the MRF fan. Whereas it remains kind of exactly the same with the lumped fan. And then so there's kind of an example here. The swirl looks a lot different, and that's essentially the comparison between the MRF fan and the fan object. And this is kind of a situation where you have everything kind of packed close together. So the velocity right close to the fan is not going to be completely physical, and so that makes a big difference here. And then for thermomechanical coupling, this was kind of an example of using that for ANSYS. So ANSYS has really nice kind of data mapping with the imported load capability, and you can do kind of all sorts of validation and stuff on that, like reverse mapping. There's an example with a BGA. It's kind of a forced convection of a BGA is modeled, and the geometry is created in Icepak. And the geometry is brought into mechanical and simulated simply, and then you can kind of do a submodel to look at what the at the solder ball, individual solder ball there. So that's kind of what that looks like. And yeah, so in conclusion, stay ahead in challenging times. Contact us at info@ozen.inc for any of the following services. Software sales, tech support, training, consulting. And to purchase or contact ANSYS or other software, please contact us. And if you would like to have a demo, please let us know. And if you have any questions, please let me know. So yeah, thank you for your kind attention. And that kind of concludes the presentation part of the webinar.
Any questions?
There's an online question. So for the MRF, you can only use it for axial fans, and that's actually not true. You can use it for blowers as well, and that's actually something where it's that the blower is not really possible to simulate. With the current fan object, you can't really do that with the fan curve because all the flow is kind of circumferential. So you can use a non-axial fan for MRF, and actually there is an example of that shown in one of the pictures. Yeah, over here. So yeah, this on the left over here, that's definitely not an axial fan, and it's simulated because we have this 3D CAD of the fan here. That's the moving reference frame representation. I mean, not moving, multiple reference frame representation of the fan there. So it's not just for axial fans. So are there any other questions? I'm just going to answer this question just online here. All right. Well, I think with that, I'll end the webinar. Thanks to everybody attending in-house and online, and have a good day. All right. Bye and take care.
Thanks.
Thank you.
All right.